So thank you very much for your invitation. I'm happy to visit laboratory of combinatorial and geometric structure because my talk will be connected to combinatorics and combinatorial methods. On the other hand, on the other side, it will be geometric motivated topic, primarily it's motivated by algebraic geometry. So let's start, and I would like to say some words about so-called minimal model program. The minimal model program, abbreviated just MP, so can be expressed as follows. So you have F, a finitely generated field, finitely generated field extension of the complex number field, and the main goal in this minimal model program is construction of a good projective algebraic variety X. Good should be explained, such that this the field of rational function on X is isomorphic to given field F. So I write down the field of rational function on the algebraic variety X, just C of X, and it should be isomorphic to field F. So this is situation that where algebra meets geometry. So F is an object of algebra, and X is an object from geometry. And it turns out that we have many possible solutions of this problem, the problem of finding such a projective algebraic variety. But we would like to choose from these all possibilities something good from different point of views. So we want to find a good projective variety X, and this goodness will be measured by properties of canonical divisors. It's a special class of subvarieties of codimension 1, canonical class, and also it's measured by possible singularities of X. I mention here that singularities appear mainly unavoidable in dimensions starting from dimension 3. So in low dimension 1 and 2, one can get good modules which are non-singular projective and actually uniquely determined. But starting from dimension 3, such a module cannot be chosen uniquely, and this is a difficulty. And moreover, as I already mentioned, there's possible singularities. Sometimes there will be unavoidable singularities. So,
я так читал, что для кривых это всегда можно выбрать модель гладкую, а для двумерных многообразий, для поверхности это тоже возможно. Это новая теорема.
Yes. No, it's not a new theorem. It's true that a smooth projective module of a curve can be constructed purely algebraically, just from all possible discrete valuation of this field F. So the field of function and all discrete valuation which are trivial on the constant field C, they give a geometric object, and it will be a projective smooth curve. In the next dimension 2, there will be many possibilities to find such a geometric smooth projective module. And the reason is that we can choose one smooth projective module and then blow up points. And blowing up a point on a smooth algebraic surface gives another surface which is birational to our original one, so the field of function will be the same, it remains unchanged, but the corresponding variety x will be somehow more complicated. And exactly already in this dimension we can say, well, we don't want to blow up something what is too many, so we want to find an opposite situation, so a model such that it's not obtained from blow up of another smooth surface. And it's possible that in dimension 2, for any field of transcendent degree 2 over C, we can find such a model, well, and under some restrictions, so I will say when it is unique. So if it depends on the canonical class, but there is a minimal model and it's unique, so that means it will be surface which has no exceptional curves. Exceptional curves, it's a rational curve on a surface which can be contracted to smooth points, and this contraction is the opposite to blow up of a point. So we can go to some surface which contains no exceptional curves, so we cannot contract these curves remaining in non-singular surface. And the problem of existence of such a model, it was already solved more than 100 years ago. It's by Italian geometers. So, and classification of algebraic surfaces also is based on this kind of procedure. So to find, so any surface which has non-negative codairy dimension, I will say some words about it, has such a minimal module. But the question is in dimension 3 and higher, and this problem started to investigate it in algebraic geometry maybe from the end of 70s. So the group, of course, some steps have been done by classic Italian school, but not on the base of Grothendieck and other foundations. So starting from end of 70s, beginning of 80s, previous century, so the people become interested in what happens in high dimension. And this was the origin of minimal model program or Mori program. So many people were involved to understand how to construct these good models in high dimension. And for the dimension 3, the important contribution has been done by Shigefumi Mori, and he got Fields Medal 1991 for his work, especially existence minimal model in dimension 3. But the situation in high dimension, dimension 4 and higher, demanded more time. So only several well, decades later, some progress has been obtained. But for my talk, it will be interesting the following. So I go to next slide. I would like to stress in this connection the role of hypersurfaces. So if we look at finely generated extension of the field of complex numbers, so we can realize this field as extension. So with only as extension with only one relation between generators. So that means algebraically or geometrically, algebraically it means that the field F, if it has the degree of transcendence say d minus 1, then one can find exactly d generators of this field, which are related by relation. This relation can be it's a polynomial relation, so we can realize this field as a as a function field on some hypersurface in affine space. So here I wrote in this, it's not correct, parenthesis, so I mean that on this hypersurface the field of function is exactly our given finely generated extension of field C. So of course it's possible, but the problem that the hypersurface, which equation for this hypersurface may define rather bad algebraic variety. So it may be singular, it may be also non-normal variety, and this is not, and of course we need also to get a projective model, because in this description we have only a affine hypersurface. But nevertheless, hypersurfaces is a very important class of starting point for investigation this problem of finding minimal models. And I would like to consider in my talk a rather special class of hypersurfaces, and I would like to show that for this special class of the hypersurfaces one can solve minimal model program by combinatorial methods. And let me explain some examples of hypersurface I would like to work today. So I would like to consider the polynomial that appear in this description of field F. So the polynomial will be F small. I would write it as a sum of monomials. So it's the sum of d plus 1 monomials. And this mi, these are exponents of these monomials. We can look at these exponents as lattice vectors, so m0, m1, md. They are lattice vectors and this semigroup n to the power d. Well, and I would demand that as lattice point, as point with integer coordinates, they should be affine independent. So affine independent, this is a condition, and one can express this independence very explicitly using linear algebra. So we have d plus 1 vectors with d coordinates, and we add to each vector additional coordinate 1 at the beginning. So we get d plus 1 lattice vectors. And affine independence actually is equivalent to linear independence of the matrix with rows obtained by in this way. So that means we get matrix with integer coefficients and should have non-zero determinant. This is the condition for this special class of polynomials, and I would like to say that the polynomials are determined by just discrete data. We need to fix this matrix, and this matrix defines a polynomial which relates d variables, and it determines a function field f. So the algorithm of finding minimal module will work perfectly if I consider such kind of polynomials, but one can also consider more general class of this polynomial. So for simplicity, so for illustration, I gave some examples of these polynomials. You see it. Sorry? I explain what this means more general. Of course, in this situation, what we can see, if we take exponent appearing in this polynomial, they give us a set of lattice points which are vertices of simplex, lattice simplex. So this is in this case it's a dimensional simplex. Here is a triangle with here is also triangle, but it will, so maybe these are three examples of triangles, but different kind of triangles and different properties, and so the field will be, of course, have different properties, and geometrically corresponding varieties will have also different properties. So these are examples of this special input data for finding minimum. But, well, as I said, my aim, two times it's misprint, is explain a simple combinatorial algorithm for constructing projective minimum module of arbitrary special hypersurfaces that I already mentioned, and compute their invariants. Geometric invariants I want to mention is a codiary dimension, topological Euler number, or some other Euler numbers associated with this variety, also Hodge numbers, also some other invariants can be also computed, but I'll restrict myself to probably Euler numbers and not to Hodge numbers. So important is that the algorithm works, as I mentioned, for more general family class of families of hypersurfaces, and they are called non-degenerate toric hypersurface. I explain the appearance of toric hypersurfaces. So the reason for that comes from toric geometry. So first of all, I would like to say we started at the beginning with a polynomial, just usual polynomial in d variables t1, td. But the ring of polynomials, it's a subring of Laurent polynomials, where I inverted these variables t1 and td. So we can say we did a localization, we localized by some elements this ring. We get a little bit larger ring, but the set of points will be smaller, and this new ring it corresponds to algebraic variety, which is a torus. So this larger ring describes all regular function on algebraic torus, which is a C star to the power d. So elements of this ring are Laurent polynomials. So it's a sum of, and I would like to extend the class of these special polynomials to this kind of sum. So at the beginning I took only non-negative exponents, but now I would like to extend and allow this exponent to be with negative coordinate, and the same condition that this exponent must be affine independent. So for this class, it's again, so everything for this class depends only on the matrix with entries M0, MD. So, but in this case, entries belongs to the lattice z to the power d, with possibly negative coordinates. So now next, what I also wanted to mention, so I consider possible transformation of this matrix, which actually leaves unchanged our up to isomorphism, the set of zeros. So this is to any integral valued matrix from the group GLDC, we obtain an automorphism, regular automorphism of the d-dimensional torus. This is a torus, and this automorphism determined by d, regular function, actually invertible function, which comes from the coefficient of this matrix. As soon as we have invertible integral matrix, we can use this matrix to transform algebraic torus C star in some way by monomial coordinate change. This is one transformation. Another transformation that we can do, we can, and it's the transformation of polynomials. We can choose a vector b1, bd, and take a monomial t to the power b, and multiply a polynomial f by this monomial. Since
это унимодулярные матрицы.
Exactly. This is a unimodular, the group of unimodular matrices. They are invertible. That means determinant of this matrix should be 1 or plus or minus 1, and then we can invert in integral way, and this shows that such a transformation, that we have coordinate transformation, these are new coordinates, so they are monomial transformations. So we can transform a coordinate. Using this transformation, we change also our polynomial f on will be. And another possibility to change our polynomial is just to multiply by monomial. Of course, there will be another polynomial, but it doesn't influence on the zero set of this polynomial. So we get so the hypersurface in the torus, that is toric hypersurface, will be isomorphic. This is what happens. Well, and next what I want to mention, I would like to use some theory which is rather useful for beginners who want to learn algebraic geometry. Learning algebraic geometry, one needs not only abstract definitions, but also some examples where one can see how this definition work. And I suggest and all participants of the seminar to try to use toric varieties for this purpose. So what are toric varieties? So toric varieties are some varieties with action of torus, so their compactification of torus. They may be affine, quasi-affine, quasi-projective, even projective. And examples of toric varieties are affine spaces, or projective spaces, or product of projective spaces, and some other. Important is that on these varieties there is an action of torus, and the torus has a dense open orbit which is isomorphic to itself. So it's a variety which contains torus. The torus acts on itself by group multiplication, and this action on this open subset can be extended on the boundary, so to say, and, in a regular way. So this is how every toric variety can be obtained. Smooth toric varieties can be also easily described as gluing affine, so smooth projective toric varieties can be obtained by gluing affine spaces using monomial coordinate change. So you can easily see that standard atlas on projective space consisting of D+1 charts, affine charts, so they coordinates in these charts transform by monomial using some unimodal matrix, so it will be monomial change of coordinates. And the same happens for any toric varieties. So starting from dimension 2, there are countably many non-isomorphic toric varieties, even smooth, and this class of varieties are very useful from many. There are many applications of this class of varieties. But today I will be speaking about minimal model program. So why I need toric varieties? So I start with affine hypersurface in torus, and I will construct minimal module of this affine hypersurface by taking Zariski closure in some toric varieties. The hat, it will be toric variety containing this torus as an open dense subset, and as soon as we have something in this open dense subset, we can just take a closure. And it turns out that the solution of finding minimal model program actually can be obtained by appropriately choosing this toric variety, ambient variety. So and now it remains to explain how to construct toric variety such that the closure of hypersurface, affine hypersurface, will be a good projective model. For this, I need more general statement. So first of all, I would like to say that in our example, the exponent, for special polynomials, the exponent, which are affine independent, they can be interpreted as vertices of d-dimensional simplex, and we can call this simplex, traditionally it's called Newton polytope of the polynomial. In general, Newton polytope is a convex hull of exponent of monomials that appear in the equation of toric hypersurface described by polynomial f. But we need some additional non-degeneracy condition. Well, the algorithm I will be speaking depends actually only on this Newton polytope. In our special situation, I don't need to say many words about non-degeneracy condition. It will be automatically satisfied. And the algorithm as input data need only this lattice simplex, and everything then works in a very explicit way. So that, and the general algorithm will be also purely combinatorial. So everything will be depending on Newton polytope of the polynomial equation of the hypersurface. So let's say something about toric hypersurface. I would like to say that if we take a special hypersurface, that means sum of monomials, we can then, and I would then the volume of the simplex multiplied by d factorial, it actually equals the absolute value of determinant of matrix B that I already mentioned before. So we have matrix where we order d plus 1 times d plus 1, where we added additional 1 as the first coordinate. So exactly this matrix, determinant of this matrix describes the volume multiplied by d factorial. And moreover, so if we look very special at very special hypersurface where all variables, here I use it, x, well, okay, x1 plus d plus 1 is 0, then it's easy to see that the corresponding hypersurface will be obtained from deleting from affine space d plus 1 coordinate. It will be affine. It will be linear hypersurface, linear, and it will be. So that means the whole equation defines linear subspace in CD. So the zero set will be d-dimensional affine space, but we also should not forget about non-vanishing of all these coordinates, and so we should delete from this d-dimensional one-dimensional affine space some hyperplanes, exactly d hyperplanes. Well, in special case, I already mentioned in my previous lecture, one obtains, for example, a fine line minus 2 points, or projective line minus 3 points. Well, important is that the Euler number of special hypersurface can be computed, it's a topological, very easily from determinant of this integral matrix B. It will be up to sign. The sign will be minus 1 to the power d plus 1, and here d factorial of standard volume. It and it actually holds for large class of Newton polytopes. So for in the case of simplex, one can easily show it using elementary topology, but it's true also when the polynomial f not necessarily of special types. It's enough to have such a polynomial non-degenerate. So anyway, so this invariant volume of polytope multiplied by d factorial will be always positive integer. One can prove it, and up to sign measures of Euler characteristic of affine hypersurface intervals. So this was this result was has been shown by Hovansky end of 70s, and also I believe it's considered by Bernstein and Danilov and some other mathematicians from the school of Arnold. So now I would like to concentrate on the algorithm, and for this I use some notation from the theory of toric varieties. They are combinatorial notation. So I need two lattices. One lattice is will be denoted by M, another lattice will be denoted by N. It's a dual lattice. We have two real vector space, MR and NR. And we have a pairing between these two lattices and two spaces. For lattices, this pairing has value in Z, and for corresponding vector spaces, there will be values in R in reals. So generally, we start with some finite set A, and take and assume that finally this subset generates the whole space. So that means using affine combination, we can get any point with the real coefficient. We can get any point of this space, and that means that the convex hull of this set will be a polytope, and actually it will be a lattice polytope. The vertices of this polytope will be some of the elements from this finite set. So it will be full dimensional lattice polytopes, that means maximum dimension D. And moreover, I will use some piecewise linear function on the dual space, which I do not in this talk like minimum on P. P will be polytope. So this function send every element y from this space to minimum of this linear function on the polytope. So as I said, this function is the arguments of this function are elements of this dual space, and these elements of this dual space are linear functions, so they can be minimized on the compact subset P, and this minimum, this is a value of this function that I want to consider. It will be piecewise linear because minimum will be attained, of course, at some vertex, but it can be attained on some edge or even codimension one faces. So, and if we vary element y, then the set of where minimum will be attained will be changed, but it will be in some convex way to change some good way. So then at least continuous and also convex, described by convex function. So what I want to say just about combinatorics, the polytope P can be described as an intersection of half space. So we have a lattice polytope. We can take arbitrary non-zero lattice point in the dual space, dual attached, so space where corresponding to dual lattice n, and then minimize this element on the polytope, and consider linear equation, scalar product greater or equal this minimum. And if we do it for any possible any elements of this dual space, we actually will get polytope P as intersection of countably many half spaces, linear subspaces. But in fact, only finitely many half spaces are essential to describing this polytope. Actually, in this case, it's enough to consider half space coming from vectors that are minimized on codimension 1 faces of the polytope P. Well, and next important ingredient for solving minimal model program, aim of minimal model program is the notion of fine interior of polytope. The fine interior of the polytope is the set of points in our space where the polytope P lives, but we, instead of inequalities above, we consider a stronger inequality. We add additional +1 here, and that means that we somehow shift our half space in the internal dimension, so by the integral distance 1. So it's important to remark that these are integral vectors, but the polytope in general need not be integral polytope. We can use this notion for sufficiently large class of polytopes which are not lattice polytopes. But anyway, we get again some convex set because it's intersection of, it will be compact because it will be bounded, and it will be convex as an intersection of convex half spaces. But moreover, one so it will be actually a compact, but we can also say something more. First of all, I would like to reformulate description of this set as a set of points in the original polytope P, x in P, and the condition that I put here in inequality I interpret as a some kind of distance, measuring of distance between this point P and the codimension 1 codimension 1 phase, or some integral subspace. It's not necessarily coming from the codimension 1 phase, but it's important that we have integral supporting hyperplane of the polytope P. That means a hyperplane that describe the boundary, boundary of a fine half space where this inequality becomes equality. So there is one more remark that I would like to formulate here. Any interior lattice point of the lattice polytope P automatically belongs to this fine interior. It's very easy to see because the minimum on the lattice polytope of integral valued linear function will be some integer, so this will be minimum. And if I add +1, it will be also integer, but since the for an interior lattice point the integer minimum will be strictly larger, then it will be at least difference 1. So this inequality will be satisfied for all interior, strong inequality will be satisfied for all interior lattice point. So that means interior lattice point of the polytope, this is a set, will be contained, and automatically convex hull of these interior points will be also contained, because, as I said, fine interior is a convex subset in fine interior. Here I give you a picture of computing fine interior in the case of dimension 2. One can show it's not difficult that for any two-dimensional polytope, the fine interior, lattice polytope, the fine interior, it's exactly convex half of the set of interior lattice points. So you can see this picture. So we start with polygon with 4 lattice vertices. So it's a yellow picture, and then so we take some direction depending on this value choosing of vector nu. For this direction it's vector 1 1. So and then we minimize and obtain boundary line touching our polygon at some vertex, and then we move this line inside by 1, and this is explained by this adding +1 in the equation. So that means we consider a half space bounded by this moved line with this boundary, and we should do it for all possible integral half plane supporting this polytope. Well, as a result, we get the polytope with 7 vertices. You can see, and it's exactly the set of all convex half of all interior lattice point. As I said, it's a small theorem, but it's not difficult to prove. In particular, you can see that some of sides of this polytope are parallel to sides of original polytope P, but there are some also sides which are not coming from the sides of enveloping polytope. So that means you cannot get fine interior just only moving codimension one side. You can do it. You can do sometimes more. And I would also to mention that in dimension 2 we have this equality. In particular, it follows from the equality that if the interior lattice point is empty, then the fine interior will be empty. So the fine interior will be not empty, if and only if in dimension 2 when we have interior lattice point. In high dimension, it's not true anymore. So we using
yellow polytope,
it's P. It's P. And the lattice M is just lattice which is described here by standard. So this standard lattice z to the power 2. M is just z to the z2. It's like z2. It means z plus z. It's a lattice of we consider yes, it's a lattice of rank 2. M is lattice of rank 2. So I hear it when I write down this expression. I mean I take M is just z to the power 2, and lattice positive. So everything is on the plane. And take a convex hull. In dimension 2, this is the way how to produce a fine interior. But in high dimension, it may happen the following. You have lattice polytope without interior lattice point, but the fine interior is not empty. It will be rational. In general, it's a rational subpolytope. It may be like one rational point or one rational segment. So there, already in dimension 3, fine interior, this equality is not true. One have only inclusion. The right hand side, it's a it's a subset of the fine interior, but not necessarily the whole fine interior. So the right hand side may be empty, but fine interior is not empty. There are examples already in dimension 3. But in dimension 2, it's an equality. Yes, the idea of fine interior was invented by Jonathan Fine. So he wrote a thesis in 1983 at University of Warwick under guidance of his teacher Miles Reed, and who mentioned results of the Fine in very famous paper, Young Person Guide to Canonical Singularities. But Jonathan Fine, when he wrote his thesis, he stressed that he was very strongly influenced by Danilov and Khovansky, especially Danilov survey on toric varieties published in 1978, and Khovansky paper which contains some computation of geometric invariance of hypersurface, even and complete intersection using Newton polyhedra. So these two papers were used as motivation in the work of Jonathan Fine. Well, Jonathan Fine suggested this notion, and in his thesis he called f of p the heart of the polytope p. So something which contained inside. But Miles Reed decided to mention this notion, combinatorial notion, fine interior. Yes, yes, yes. And interesting that this notion that did not didn't have continuation. So many years after, there was no any mention on this, and so this notion was forgotten. Although the person like Miles Reed was one of founder of and contributor of minimal model program, and he also probably had in mind that this notion can be applied to minimal model program, but it hasn't been done.
So, Miles Reed это минимально для торических многообразий или вообще?
Miles Reed has written a paper devoted to Grothendieck's 60th birthday about toric geometry and about toric singularities and some kind of factorization of birational morphism of toric varieties, but not for hypersurfaces. This is and in this this very also well-known paper of Miles Reed, there was no discussion of hypersurfaces. The hypersurfaces was discussed in the thesis of Jonathan Fine, but Jonathan Fine after defending his thesis, left mathematics. He worked all his life in some applied mathematics, and well, today he is retired, and he gives lectures on some very advanced course on Latic program. But he's a good specialist in computer science. Of course, Miles Reed continues algebraic geometry, but he did not follow his idea of his student. Of course, that's true. Yes, it's true. So this is what now I would like to say some. Oh, time is running. Well, lattice polytopes that I would like to consider, there will be Newton polytopes of so-called non-degenerate hypersurface in algebraic torus. So algebraic torus can be simply described as a group of homomorphism of the lattice M. This is free abelian group of rank D to C star. C star, it's a multiplicative group of complex numbers. So as a result, you get isomorphism with C star to the power D. So the Laurent polynomial is just finite summation over some set of exponents, and we use these Laurent polynomials with some additional open conditions. So the coefficients that appear here in this as coefficients of the Laurent polynomial Am, they should be not be chosen in special way, somehow general way. But let me explain these other lattices from point of toric geometry. So M, this lattice, can be, in other words, considered as a lattice of characters of this algebraic torus, d-dimensional torus. And N, the dual lattice, is a lattice of invariant variation or one parameter subgroup of the algebraic torus. So these are this is the meaning of the two lattices that I already mentioned. Now we come to this condition non-degenerateness. So a Laurent polynomial, so it's a finite sum of monomials with Newton polytope P, is called non-degenerate if for any phase the affine hypersurface defined by zero set of this another polynomial. You see, I instead of take summation over all set A, I consider only those exponents that belong to phase of this polytope. Of course, it will be also polynomial in general in D variables, and it determines hypersurface, and this hypersurface must be either smooth or empty, and smooth in a sense, so the smooth that as a subscheme, so that means the variety described by this equation should be as a subscheme reduced. So there is no multiplicity, like the multiplicity of a root of a polynomial. So this non-degeneracy condition on the coefficients, it's a risk open condition, as I said. We can consider this set of coefficients as a point in some affine space, and in this affine space the polynomials that are defined the risk non-degenerate polynomials are defined they define open subset. So Now I want to say about this Bernstein-Kushner-Renkel theorem. I already mentioned it in special case, but it's true in a general case. So for any non-degenerate hypersurface with Newton polytope P, the topological Euler number of this hypersurface can be computed just from the polytope as a normalized volume of this polytope and with a sign -1 to the power d minus 1. And the Hovansky theorem was also about the geometric genius of this hypersurface. It's a birational invariant. It describes dimension of the space of differential form of top degree on any smooth model, and it also can be computed explicitly and combinatorially as a set of interrelative points in the polytope. So there are two results already known in 70s. Well, but now I would like to say something about singularities, because we cannot avoid singularities, as I mentioned, for minimal model program. So there is kind of measuring of singularities for on normal, irreducible, quasi-projective, and Q-Gorenstein algebraic variety. So how did it can be done? We have such a varieties. Q-Gorenstein means that the canonical class is a Q-Cartier divisor. Normal is usual. So assume that we have a resolution of singularities whose exceptional locus is the union of smooth irreducible divisors with normal crossing. And we consider in this set for these divisors, then the canonical class of this smooth variety Y can be related with the pullback of canonical class on X with using some linear combination of these exceptional divisors. So it's a divisor where the morphism is not isomorphism. It will be birational morphism, but along some divisor it will be non-isomorphic. This divisor could be contracted to singularities. These coefficients that appear in this linear relation between two canonical classes, they're called discrepancies, and they are in general rational numbers. But for minimal model program, we need to consider rather good singularities, and they are the best singularities are terminal, where discrepancies are strictly positive, or canonical, where discrepancies are non-negative, and there is a called log terminal singularities, where these coefficients are strictly greater than -1. These are three kind of singularities that naturally appear in minimal model program. So now I would like to define what is minimal model. I gave at the beginning a vague feeling of that, and now it's a precise formulation. So a normal projective variety with at most q factorial terminal singularities is called minimal model if the canonical class is a semi-ample Q-Cartier divisor. This is okay. This definition used many notions from algebraic geometry, but it's very natural, and it was known already in end of 70s. Also, this is what people are looking for in dimension 3 and higher. So such kind of birational models. And existence of these birational models was not easy to show. So, but it can be rather easily and combinatorially can be done for non-degenerate toric hypersurfaces. And this is exactly the topic of my talk. not only existence of this minimal model, I would like to mention there is then some natural topological invariants of minimal models, and I call them stringy Euler number because it will be different from usual Euler number, topological Euler number, and actually it's very sensible invariant which feels existence of singularities. So for defining such a Euler number, one used this formula relating to canonical classes X and the resolution of Y of X, and also some divisors and which are assumed to be normal crossing divisors, smooth subvarieties normally crossing. And the formula for this Euler number can be combinatorially written in this way. It's a summation over O but subset J in set I. I is a number, a set of numbers parameterizing these divisors. And as soon as we have chosen such a subset, we can take an intersection of these divisors. It will be smooth, projective subvariety or empty set, and this topological number is well defined, is classically well defined, but we need to multiply it by some product, some rational numbers. And surprisingly, and it's not so easy to see, this number will be independent on choosing resolution of singularities of variety X. So we can take different kind of resolution, but result will be the same. This is very convenient invariant in algebraic geometry, motivated by physics. So Stringy, this is the reason why we have this Stringy Euler number, and it appeared from mathematical understanding some formulas of physicists motivated by in string theory. So some properties of this string invariant. So it's, as I mentioned, it doesn't depend on the choice of the singularization. And in particular, if X is smooth, then this stringy number coincides with the usual number. Moreover, it's also good behaved if we have a so-called crescent resolution. Crescent desingularization can be characterized by vanishing all discrepancies. Such a morphism appear already in the case of surfaces theory. So the stringy Euler number of X, singular variety, coincide with usual topological Euler number of Y if this morphism is crescent. That means that all divisors in the relation have coefficients AI equals 0. And moreover, if two varieties are so-called K equivalent, birational K equivalent, so they, for example, for varieties birationally equivalent Calabi-Yau varieties or some other K equivalents can be precisely formulated by then the stringy Euler numbers, the string invariant will be the same. So the topological Euler number behaves not so good, but stringy very good in this birational geometry. And there are two, so there is the formula for this, actually another formula for the stringy Euler number using locally closed stratification. So we can use stratification by locally closed subvarieties. So we take an intersection divisor and take complement to in each divisor to closed subset coming from other divisors. And there is another equivalent description of this stringy Euler number of singular variety. So X is singular, but nevertheless, we can define all the number of such a singular variety. As soon as we have singularities which are not worse as log terminal. So, so the important properties of this string or the number, as I already mentioned, is so if x and x prime are two birational minimal varieties, then this number or the string or the number are the same. For topological, it's not necessary, as I remarked. So for usual, this equality doesn't hold in general. This is the reason. Now I would like to mention. Sorry, my talk becomes longer. I mentioned already 2 days ago the notion of reflexive polytope. So there is a notion of polytope. So the dimensional polytope containing 0 lattice point of lattice M in its interior, and it's called reflexive. If the polytope, it will be denoted by P star, is also a lattice polytope. So original lattice polytope, it has a 0 inside. We create in the dual space another polytope P star, and it will be and we demand that it's also a lattice polytope with respect to dual lattice. And this is a definition of reflexivity. So how to construct such polytopes? I would like to explain that we can construct reflexive simplices just from a Diophantine solution. Take the following Diophantine equation. The sum of 1 divided by k0, k1, and kd equals 1. One can show that this equation with respect to k0, k1, kd has in each fixed dimension d only finitely many solutions. And as soon as you have such a solution, there is a possibility to write down, to create an equation and construct reflexive d-dimensional simplex. It will be Newton polytope of some quasi-homogeneous polynomial, and this is how this polynomial can be written down. So let's consider a very important combinatorial duality for reflexive polytopes. So for reflexive polytopes, the dual polytope will be also reflexive, and if we apply again the star operation, we come back to our original polytope P. Moreover, there is one-to-one correspondence between k-dimensional faces Q of first reflexive polytope and the complementary dimension the d minus k minus 1 faces Q star of the dual polytope. The dual face can be described explicitly. The face due to Q is Q star. It's a set of elements in the dual polytope satisfying these equalities. And moreover, I already want to stress that the combinatorial duality between reflexive polytopes P and P star perfectly agrees with prediction of mirror symmetry for minimal model of hypersurface, toric hypersurface associated with these polytopes as Newton polytopes. In particular, one can show combinatorially that the string, if we take a toric variety associated with polytope P and toric varieties associated to dual polytope P star, and take a closure of, so of course at this point I use some part of the theory of toric varieties, that we can construct toric variety to every lattice polytope. But if we have this toric variety, we can take a closure of toric hypersurface, and we can do it for P and for P star. And it turns Yes, there is a closure. Yes, there is a closure. So and it turns out that the stringy Euler numbers of this singular, possibly singular variety, Calabi-Yau variety corresponding to first polytope, differs from the stringy Euler number of the Toric variety, Calabi-Yau, maybe singular, corresponding to dual polytope. They are equal up to sign. This sign depends on the dimension, but it works in arbitrary dimension, d. This is a very natural property topological test of mirror symmetry for Calabi-Yau varieties in arbitrary dimension. And first one, I think, appeared in the paper of Waffer and Witten. So now I would like to say that the construction that I want to mention today appeared actually in some very special situation when we consider reflexive polytope. So in paper published in '94, my paper, I did it for the case of when polytopes P were reflexive, and in this case this closure of toric hypersurface, this was a Calabi-Yau variety, this variety with geometric genius 1, and actually with trivial canonical class, that construction, and it has probably canonical singularities, but one can resolve singularities using some simplicial subdivision of normal fan of this polytope. So what one get another toric varieties and another closure, which I called Z hat, and this closure was a minimal model of possibly singular Calabi-Yau hypersurface. And for this, and the morphism between the canonical model Z bar and Z hat was crepant. That means the corresponding Euler number remain unchanged, and it was possible to see these equalities. Remarkably, in dimension d equals 4, we get Calabi-Yau threefolds, and these varieties become, they appear, one can prove that they are non-singular. So the dual Calabi-Yau and original Calabi-Yau minimal model, they are non-singular three-dimensional Calabi-Yau varieties, and they satisfy all predictions of physicists. So in this, using this duality, one can construct examples of minimal mirror symmetry in arbitrary dimension, and see that mirror symmetry exists. So just purely combinatorially. So sorry if you want to stop me, please. But stop me. If you are not so tired, I would like to explain what happens beyond the reflexivity and meets.
You mentioned some people beaten with someone else, but they didn't prove anything. They just predicted.
They predicted. So the prediction was already at the late 80s, and there are some some examples and computations, but computation not from mathematical point of view not very satisfactory. They needed to be justified, and moreover, the construction of mirrors at the moment was known in the language of combinatorics. So the contribution was to see that it can be formulated just as duality for polar duality for reflexive polytopes.
Was it helpful, the predictions, so you could do it independently?
it was helpful for physicists, very.
For physicists,
Yes.
but for
For mathematicians. Yes, it was helpful because one can use many tools from toric geometry. To this time, there was a very nice theory of hypergeometric functions and hypergeometric differential equations developed by Kapranov, Zelevinsky, and again found Kapranov and Zelevinsky, and it turns out exactly this class of differential equations are necessary to describe quantum deformation of the in the quantum cosmology of Calabi-Yau varieties, and compute, for example, a number of rational curves on a quintic threefold, and to justify that this prediction of physicists, Candelas, De La Oza, Green and Parker's, it was in a paper of Nuclear Physics 91, published in for mathematicians, it was very surprising that physicists could compute invariants which were beyond the possibility for mathematicians using mirror symmetry. And at the same time, mathematicians started to think about mirror symmetry and to formulate it in a different way. The homological approach to mirror symmetry initiated by Maxim Kontsevich. And I suggested combinatorial approach, and physicists really found many examples supporting, so they are now absolutely convinced that this duality is exactly what mirror symmetry expected. It was expected, and they did computations and many verification of predictions. So that means that different kind of theories come together, but not only. So I used also Daniel Khovansky results about for computing Hodge numbers, and what I want to mention, after appearing this mirror symmetry, combinatorial mirror symmetry, I discussed with Shihoko Ishii, so mathematician from Japan, that this construction of minimal models for Calabi-Yau should have some analogs in arbitrary dimension, and it turns out it happens indeed. And I not so long ago I was succeeded to reformulate the result of Ishii that allows to compute code-Avery dimension of toric hypersurface in terms of in combinatorics. So non-negativity of kappa of z, code-Avery dimension, holds non-negativity holds exactly when the finite theory is not empty. So in this case, we get we can expect to get minimal model. But how to construct this minimal model in general? It was a recent paper of mine. And I use other combinatorial object. I mentioned it. It was a finite support of finite interior. It's number of some finite set of lattice vectors in the dual space. So that satisfies this relation. So the minimum of on a finite interior on a P differs by 1. There are only finitely many such vectors. So these vectors use to create one-dimensional cones in the fan sigma hat. Sigma hat is a fan defining toric variety where I must take closure, Zariski closure, and to get minimal module. And then one should construct actually simplicial fan sigma hat whose one-dimensional cones exactly generated by this set of vectors. And for this, one need, so these are examples of this fine interior, dual polytope, and support of this fine interior. These are vectors on the boundary. And it was done, for example, in this case, for Laurent polynomials in two variables, t1 plus t2, and product t1, t2 to the power minus 1. So this is one example how it works, this notion. But there is a third notion that I use. It's called canonical how of a polytope. So canonical how is determined by inequalities, but finitely many inequalities. We consider this inequality, natural inequality, not only for those vectors that belong to the support. What we get will be rational polytope containing P. And in small dimensional, like if the polytope is two-dimensional, then the canonical how coincide with the polytope itself. But in larger dimension, it's not true. And 2 days ago, I formulated the conjecture that it should be a lattice polytope in dimension 3. Well, it's still open how to prove it. But now I would like to explain the algorithm. For algorithm, we should use two polytopes, F, P, fine interior, and the canonical and how. And then we construct a new polytope P tilde, which is a Minkowski sum of these two polytopes. Everything can be done under the condition that the fine interior of P is not empty. Only in this case we can expect to get a minimal module. And so as soon as we have this polytope, we can construct toric varieties associated with this polytope. And it turns out that this toric variety has a rather good singularity. The singularities are canonical, and moreover, one can find a crepant toric morphism that there is toric variety corresponding to polytope. It's V tilde, and there is a toric variety V hat defining crepant morphism. Similarly as in the case of reflexive polytope, but it works for arbitrary polytope as soon as fine interior is not empty. And it turns out that the Zariski closure of toric hypersurface in this constructed toric variety will be minimal module. So this is the construction. So it was first appeared 2 years ago in the preprint. Now it's the paper is accepted for publication. So it appears soon. Now next examples. So I would like to interpret the notion that I just introduced. So let's consider P. It's a blue polytope, and the fine interior in this case will be one-dimensional fine interior. It's a convex how of all lattice points, because we are in this case dimensional fine interior is 1. The non-degenerate condition can be written as follows. So it should be lambda differs from 1, but the other coefficients, so you see the Newton polytope is not simplex, it's a parallelogram. So, but Minkowski sum, it is a yellow larger polytope, so it has it's 6 gon. So, and the dual fan to this 6 gon has 6 generators. So this is 2 blue and 2 and red. But there are some other elements in support, and these are used to subdivide this fan. So we get a resolution, a crepant resolution of singularities. More complicated is coming here. Again, we're starting here. We have a triangle we have a red, it's a fine interior. And then we take a Minkowski sum. The Minkowski sum will be this complicated, 7 gold. And the normal fan has 7 generators, but then it defines the canonical model with canonical singularity. Then we can resolve singularity adding black points. So this is what happens. And of course, this is not a case of reflexive polytopes because we have many interior lattice points, not only one interior lattice point. So the application, so we can construct canonical models for any such a hypersurface from this polytope using Minkowski sum, normal fan and subdivision of this Kreppen subdivision of this fan. We can also describe so-called Ithaca fibration and see that Ithaca fibration, it's a morphism of this canonical model to some low-dimensional, possibly low-dimensional Fano variety, not Fano, but toric variety. It will be a fibration with general fibers are canonical non-degenerate hypersurface with codero dimension 0. Well, many prediction or many illustration of minimal model program can be seen from this picture, and I'm happy to see applications or some illustration of technically complicated notions just using combinatorics. And this was my idea. I also did computation for some stringy or a number of this minimal model. It can be computed by some formula, but I think I own this. It also appeared, and if, in reflexive case, it shows that this polar duality algorithm is mirror symmetry. Wow, and there is also something for the case when the fine interior equals 0. In this case, minimal model program claims that every algebraic variety of this negative codero dimension is birational to some fibration, and indeed one can see this fibration combinatorially. And something I already mentioned in my seminar talk. In this seminar talk, I use some lattice projection at the procedure when we have a lattice polytope and this lattice polytope and this polytope project on some lower dimensional polytope. So combinatorial statement, purely combinatorial statement that appears in this situation looks as follows. In each dimension D, there exists up to unimodular transformation only finitely many d-dimensional lattice polytopes with fine interior empty that do not admit lattice projection on another low-dimensional polytope with fine interior empty. So illustration can be seen in dimension D. So there are infinitely many, countably many such polytopes with empty fine interior because there is no interior lattice point, but they can be projected on the vertical line on the segment between 0 and 1, and this is the only one example. Right-hand side, it's a sporadic polytope, the only one that cannot be projected on a segment of empty segment. So any projection will have interior lattice point, and this situation that we see in dimension 2 happens in arbitrary dimension. And of course, there's a very natural question is what are sporadic example polytopes in dimension 3 and in dimension 4, and there are some candidates for this finite list of polytopes in this dimension. So there is a rather elementary way to prove it, and how to project if the projection exists. So, but I think my time is already over. Thank you for your listening.
Other questions? So this approach allows to consider certain varieties given by some certain polytopes and polynomials, and you can just, so can you compute invariants just like in Sage or Python? It should be possible, right? Do you use programming or?
Yes. I have two graduate students working in this direction. So one student, for example, looked at polytopes of in dimension 3 with exactly one interlattice point, and it turns out that in this case that there are some classes of such polytopes, actually 94 polytopes, three-dimensional polytope. They produced surfaces of geometric genus 1, because there were only one interlattice point, but with maximal coderic dimension 2. So these are interesting surfaces, can be described, and there is some interesting relation between polytopes. So they're called a Carnif surface and a Todorov surface. There is another interesting direction. One can look at special simplices in higher dimension which has no lattice points except vertices. And it turns out that for dimension 4, one can produce very interesting three-dimensional varieties, minimal module, and compute combinatorially as the invariants, because independently the problem of classification of such simplices, they are called empty simplices in dimension 4, has been done just purely combinatorially. And they were motivated also by minimal module program, but they looked these simplices somehow in a lattice which I called in my talk N. So this is, they describe some quotient singularities, terminal quotient singularity. It was a paper work of also Morrison and another two Morrison names, probably brothers. And it was interesting as a kind of singularity theory. But if one use mirror symmetry point of view, that means we consider the same polytope, but in lattice M, where we can interpret this polytope as a Newton polytope, we get interesting hypersurfaces. And this will be automatically a special hypersurface, as I started with the Newton polytope will be simplex, they will be regularity condition will be automatically satisfied. So one gets interesting example, in another point of view on classification of people working in combinatorics, just from algebraic geometry. This was further step. So I think it's interesting to look at examples to interpret many phenomena in algebraic geometry. Of course, not every algebraic variety is birational to non-degenerate high-space surface, but we can somehow replace complicated super problem of classification of algebraic varieties by classification of some classes of polytopes, and this can be done with computer. So with strong so I think that computer facilities they can bring more knowledge about algebraic varieties, because we can use this example just as physicists use experiments. So one can use numerical testing and experiments, and this was also already very successfully done by physicists. They classified reflexive polytopes in dimension 3 and even in dimension 4, and exactly for solving this problem, classification of lattice polytope, reflexive lattice polytope of dimension 4, there was developed some software packages like Polymake and Pulp. So I think it can be done not only with motivation mirror symmetry, but also minimal model program. So this is, I think, possible application. And one can somehow investigate some class of lattice polytopes and try to understand what are varieties behind this class of polytopes. And this can be the topic can be understood even by good bachelor student to do it.
Great, thanks.
Other questions? Let's thank the speaker again.
So, thank you. Thank you. Thank you.